Good morning everyone, and welcome to today's worked exam answer video. Today I am having a look at a mean bond enthalpy calculation from an AQA AS paper, which could also appear on an A-level paper, and some of you at GCSE will also need to be able to answer questions like this as well. So if you're doing the AQA specification, or if you're doing the IGCSE Edexcel triple award specification, you might also get questions like this in your GCSE papers in the summer. So I thought this therefore would be a great calculation to show you because it applies to so many people. If you are in year 12, you will be meeting this in the energetics topic of the AQA specification, which I believe you will be coming on to fairly soon, which is another reason why I've chosen to do this now. Okay, so what do we have to do? So we're told that hydrogen fluoride, which is HF, reacts with ethine, which is this C2H2 here, and they react as shown in this equation, and it says that all compounds are in the gaseous state. Now that's important because when we think about mean bond enthalpy, the mean bond enthalpy values represent breaking 1 mole of covalent bonds when everything is in the gaseous state. So that's just telling us that we can use all of the numbers in the table as they exist. In table 1, we have mean bond enthalpy data for the carbon-hydrogen bond, the carbon-carbon triple bond, the hydrogen-fluorine bond, and the carbon-carbon bond. And the ultimate outcome that we need to achieve is using the data in table 1 to calculate a value for the bond enthalpy of a carbon-fluorine bond in the product. So the easier version of this question would be that we would be working out the enthalpy change, or the change in energy across this reaction. We've actually been given that here as minus 179 kilojoules per mole, and we're using that to work out how much energy it would take to break one of the bonds. So there's a couple of things to discuss before we dive in. First of all, this delta H value being negative shows us that this reaction is exothermic overall, and while that isn't particularly necessary to know for this question, it will be necessary for other questions. So a negative enthalpy change, or a negative change in energy over the reaction, tells us the reaction is exothermic, and that means that even though we're going to need to put energy in to break these bonds, more energy has to be released when the new bonds are made. So every single chemical reaction, we will need to put energy in to break existing bonds, and energy will be given out when new bonds are made. And whether the reaction is overall exothermic or endothermic depends on the balance between those two things. So here, more energy is coming out when the new bonds are made, less energy is going in to break the existing bonds. Another thing that's important to recognise is these mean bond enthalpy values in table 1, these represent how much energy it takes to break a carbon-hydrogen bond. So one carbon-hydrogen bond will take 412 kilojoules of energy to break. Carbon-carbon triple bond, with it being a triple bond, takes quite a lot more than all of these single bonds. This is per mole of bonds that we are breaking. So in the equation, when it says 2HF, we're going to need 2 lots of the value for the HF. Likewise, if we've got the 2 carbon-hydrogen bonds in the reactants, we're going to need 2 lots of the 412 as well. The other key thing to state about these figures is, yes, this is the amount of energy needed to break the covalent bonds, but this would then be the same amount of energy that would be released when the new bonds are made. So breaking a carbon-carbon single bond requires 348 kilojoules of energy to do that. When we form a carbon-carbon single bond, 348 kilojoules of energy will be given off, and that's also important. Okay. So what's the first thing that I would do here? The first thing that I would do here is write down the calculation that we're going to do. So the enthalpy change, or the change in energy across the reaction, is always equal to the amount of energy involved in breaking the bonds, so bond breaking, minus the amount of energy released when the new bonds are made, so bond making. And the reason why it's that way round is because when we make the bonds, these values would then kind of become negative because the energy is being given off. So we take away the bond making, and then we can see whether the bond breaking being bigger than bond making, this value for delta H would be positive. If the overall bond making is bigger, then this value will be negative. And that is helpful because, as I've said, positive values for delta H represent endothermic reactions, negative values are exothermic. I'll just note that down for your reference. So at this point, we can then figure out how many bonds we're breaking, how many bonds we need to make, and we can sub that into this equation. So we know delta H is minus 179. In terms of bond breaking, what I'm going to do to make sure that I've included all of the bonds is I'm going to just cross through them as I go with this blue pen here. So on the bond breaking side, we've got one carbon-carbon triple bond, which is going to require 837 kilojoules of energy. We've then got 2 carbon-hydrogen bonds, which is going to be 412 times 2. And then we've got this 2 lots of HF. So the 2 in the front means that I could then draw another HF underneath like that, get rid of the 2 in the front, and then I can go, right, I've got 2 moles of those bonds. So again, we're going to need H to F times 2, which is going to be 562 times 2. And that's going to then be, if I work out what that is, the total energy needed to break all of the bonds. So 837 add 412 times 2, add 562 times 2. Total energy needed to break bonds is 2,785. So then that's the value we're going to put in as our bond breaking. Now I'm going to do the exact same thing with the bond making, and again I'm going to cross these off with this red pen as we go. So we've got the carbon-carbon single bond, which is 348. We've then got 1, 2, 3, 4 carbon to hydrogen bonds. So that's going to be 412 times 4. And then we've got the ones that we're trying to figure out. So we don't know the bond enthalpy for the CF bond, but what's really important is that we look at how many we've got. So we've got 1 there, 1 there. So whatever value it is, we need to have 2 of them. So this is where algebra usually comes in. We're going to say that the CF bond is equal to X. And then because we've got 2 bonds being formed, we're going to need 2x in this part of our working out. So we've got C to F times 2, and we don't know what that is, so it's going to be 2 times, and then, as I've said, I'm going to call that x. So we can still work out what we know about the amount of energy released from the bonds made for the values that we have. So 348 add 412 times 4 is 1,996. So it's going to be 1,996 plus whatever the CF bond is twice. And that's what I'm then going to put into the bond making part of our calculation. So now I'm going to do exactly that. So the value for delta H is 179. So minus 179 is equal to 2,785 take away 1,996 add 2x. And now what we would need to do is rearrange this to be able to figure out what X is. So the first thing I'm going to do is take all of this bracket over to the left hand side, and because it's a negative here, I'm going to add it on. So we're going to get minus 179 add 1996 add 2x is equal to 2785. And then I can work out what minus 179 add 1996 is, which is 1817 add 2x is equal to 2785. Then I can take away the 1817 from the 2785 to leave me 2x on the left hand side. 2785 minus 1817, which is 968. So then if I want to work out what X is, which is 1 carbon fluorine bond, I would then divide the 968 by 2. So X is going to be equal to 484 kilojoules per mole. And that is going to be my answer. Now, a couple of things. Even though we are making these bonds, and thus energy is being released, we would need to come out with a positive value when we do this calculation, because all of these numbers are positive, and that's why, like I say, we do take away the energy that is released when bonds are made, so that kind of becomes negative to represent that they're being made, not broken. But every single mean bond enthalpy value should be positive. So the fact that it came out as positive 484 made me breathe a little bit of a sigh of relief. The other thing that is good to be able to recognise is that that number seems like it fits with the numbers that we've been given. So it's kind of in between some of the values that we've got. It's not really, really low. It's not kind of like 50 or 100. It's also not really, really high. It's not higher than the CC triple bond. So that, in relation to all of these numbers, again, looks like it might be about right. Now, some of the biggest things that students do wrong here is, first of all, counting up how many bonds of each type they've got. So I'm not saying you have to cross out the bonds as you go, but you need some way of being able to count them properly. They may not give you the equation in quite such a nice format. I think at GCSE they will, potentially. At A level, they may just say we've got C2H2 plus 2HF makes C2H4F2, and then you would benefit massively from drawing it out kind of like they've provided here. So if you don't have the displayed formulae for the reactants and products, don't be scared to draw them out, because then you're making sure that you're not missing any of the bonds. The other thing that's very easy to do here is just add up the total energies for bond breaking and bond making wrong on the calculator. I've done these sorts of questions with many students over time, and they will do a calculation, they'll get the wrong answer, I'll check their working, it will all be absolutely fine, they'll redo it on the calculator, they'll get the right answer. So if you have got extra time, as in you finish your exam questions and there's time remaining, or if you do get extra time, I might suggest that this is one where you just repeat the calculation a bit later on in the exam and make sure that you've not typed something in incorrectly and that you get the same answer. The other thing that students would do wrong here is that they would understand the need to use algebra to figure out what the carbon-fluorine bond was, but they wouldn't see that it needed to be written as 2x because there was 2 of them in the product, and then they would have got x is 968, and that would have been what they thought was their answer. So always count up how many of those bonds you've got, be it in the reactant or the product, and then make it that number of x in your calculation. Okay, And if we were doing a normal version of this calculation and we had all the bond breaking and all the bond making, you would be subbing those numbers in to work out delta H. And just a reminder, if your value for delta H is positive, more energy is going in to break the bonds than was released when the bonds were made. If your delta H value is negative, like we had here, bond breaking will take less energy than the amount of energy released when the bonds are made. So if we then show that for this particular example, 1996 plus 2 times 484 gives me 2,964. 2,964 is bigger than 2,785, which is going to make delta H negative. Awesome. Hopefully that makes sense and you're happy with what I've done there, but if you are unclear with any of the steps or you want me to do another similar calculation in a video, please get in touch with me. You can leave a comment on the video or send me an email to missgtutoringandresources@outlook.com. Thank you so much for watching, guys. Have a fab day.